It's a pleasure to have the next talk with Sasha Voronov, who will talk to us about the EK symmetry of dimensional reductions of M theory. Thank you very much.
Thank you very much, David. So I will be talking about our joint work with Hisham, and it started with those two postings on the archive, and it's still going on with writing more papers. And I will be talking about, the end part of my talk will be something that we haven't written up yet, but which is work in progress. So, but I will start to add some variety to what we have seen this morning. I will start with hypothesis H, which is I know that you guys are all overwhelmed by the talks of Hisham and Urs, and it may feel like each of us, co-authors of Hisham, has their own idea about what hypothesis H is, and maybe this is very different from what Hisham has in mind. But nevertheless, let me tell you what I think about this, and start from there. So, as you may guess, the H in hypothesis H stands for Hisham, right? And so he came up with this idea in 2013, and this is the slogan is that the dynamics of M theory. Huh? Oh. Yeah. Okay. Yeah. That makes even more sense that it refers to you. Yeah. So the slogan is that the dynamics of M theory is governed by the rational homotopy theory of the fourth sphere. More precisely, if you look at the duality symmetric equations of motion of supergravity in n11 dimensional spacetime, which is thought of as the background of M theory, then we have those equations: dg4 equals 0, dg7 equals -1/2 g4 of hg4, and those equations per se define a map. From the fourth sphere, not quite the fourth sphere, but some rationalization of the fourth sphere over R, which I'm going to suppress. But the assumption, you can say that the assumption in hypothesis H is that those equations of motion in the duality symmetric formulation of supergravity in 11 dimensions come with a map from the spacetime, the 11-dimensional spacetime Y, to the fourth sphere, so that in some dual world of algebra, when you consider the de Rham algebra for the spacetime Y and the Sullivan minimum model, a certain differential graded commutative algebra associated to the sphere by rational homotopy theory, then you get a homomorphism of those differential graded commutative algebras from what rational homotopy theory associates to S4 to the de Rham algebra of Y, such that the generators of this Sullivan minimum model, M S4, here it is, the generators G4 and G7 actually map to the basic fields, form fields G4 and G7, capital G4 and G7 of M theory, of supergravity to be more precise, in the 11-dimensional space. And yeah, so in M theory, G4, you associate M branes to those form fields G4 and G7 through potentials. You first you first generate a potential for the field G4, and then the M2 brane is something that you can integrate your potential over over, like a 3 surface over which you can integrate the potential C3, and then G7 comes, gives rise to a potential C6, a 6-dimensional form defined locally in space-time, and you can integrate over it over the M5 brane. And via this map from the space-time to the force sphere, S4 becomes the universal target space of M theory, or the universal target of M theory. So one can write down this equation, which is basically the content of hypothesis H, that the pullback along this map of the rational homotopy theory of S4 is actually the same as the equation of motion of M theory in the 11-dimensional spacetime. Okay, and an amazing thing is that one can generalize this hypothesis and to reductions of M theory to lower dimensions and the reductions on Torre. The amazing thing is that this pattern continues for further reductions of M theory to 11 minus k dimensional space-time. Namely, you assume that there is some action of a torus on the 11-dimensional space-time, well, we'll assume that the action is there is a free action of the torus on the 11-dimensional space-time, and well, oftentimes when physicists work with flat space, they actually talk of compactifications of the space-time, you know, when you compactify some directions to at infinity, so that they become, instead of being R, they become S1, and this is another way of thinking of this. But we are working with the understanding of those dimensional reductions as going through modding out by actions of Torre. So what's going on is that in the generalized hypothesis H is that there is one assumes that there are those maps phi k from the 11 minus k dimensional spacetime, which is the quotient of y11 by the torus, to a certain iterated cyclic loop space or iterated cyclifications of the sphere, which I will be talking about here below, which I'm talking about below, and so that this k-fold cyclification of S4 serves as the universal target of reduced 11 minus k dimensional M theory. And so here is what those cyclifications of cyclic loop spaces are. So you first can start with the free loop space of a space Z, looking at the space of maps from S1 to Z, and then you can take the homotopy quotient of this free loop space by the action of S1, but by rotating the source S1. And if you use the Borel construction, it will be this space. And then you can iterate this construction, and this is what we are talking about. Those are the spaces, those iterated cyclifications that we are talking about. So C stands for cyclification. Yeah, here it's defined for an arbitrary space, but we are interested in the same, in those cyclifications of the force sphere. Okay, so here is a picture, sort of Hisham and Urs style, a big diagram, but it's obviously not as big as the diagrams that we've seen in the previous talk. So this kind of becomes a hierarchy of the original hypothesis H and its generalizations to dimensional reductions. That you have this mapped from the 11-dimensional space-time to the sphere, and then you mod out the 11-dimensional space-time to pass to 10-dimensional space-time. And here, physically, you are talking about the type 2A string theory. And then it comes with a map basically induced by this phi to the cyclification. And then further down, you look at another reduction, dimensional reduction, go to the 9D supergravity spacetime. And then this phi 1 induces another phi 2 which goes to the second or double simplification of the force sphere. But the amazing thing is that all the equations of motion on the 11 minus k dimensional spacetime may be read off the equations of motion of supergravity in the 11 minus k dimensional spacetime, supergravity, and actually the duality symmetric formulation of it, that is sort of pre-metric formulation of supergravity. So you can, all of these equations of motion may be read off from the Sullivan minimal model, from the algebraic gadget the rational homotopy theory assigns to this k-fold simplification. You can read off all the equations of motions from there. The Sullivan minimal model, which I claim produces those equations of motion, automatically is for k-fold simplification of any space is well known. It's classical results. So, and this I will talk about this on the next slides. So this is the example here is what happens for the type 2A string theory in 10-dimensional space. And this is as per Fiorenza, Sati, and Schreiber. So this, so we assume that there is a map phi1, which actually you don't have to assume it because it comes from the map phi. So all you need to assume is that the map phi exists, and actually Hisham in one of his papers makes an argument why this map exists. But actually from the rational homotopy theory, as soon as you have those fields in space, capital G4, capital G7, which satisfy those equations, you immediately get a map from some kind of rational homotopy incarnation of the force sphere S4, the rationalization of S4 over R. Something that you construct out of this algebra, differential graded commutative algebra. And so in principle, it might be just good enough to consider maps to this canonical map. As soon as you identify those equations, you get the canonical map phi from Y to the rationalization of S4, which has the same rational homotopy type as S4. Okay. Now, yeah. So this map phi1 then will come automatically. It will be to the simplification of the rationalization of S4, but it doesn't matter. Let's assume there is a map to this simplification of S4. And then the minimal model of the simplification of S4 is given by as this differential graded commutative algebra. These are the generators. This is a degree 4 generator, degree 7 generator. Then SG4 is another generator. It's a notation for another generator, which is of degree 3. This is a generator of degree 7. So think of S as lowering the degree by 1. And then W is a generator of degree 2. Then the equations defining the differential in this differential graded commutative algebra. So you take the differential, you take the free graded commutative algebra on those generators and then define the differential. This is what this Sullivan minimal model for the space is. Sort of being fed to us by rational homotopy theory. And the differential there is given by those equations. Some kind of equations on how to differentiate the generators and write down the answer in terms of polynomials of the generators again. But if you change notation slightly, well, first of all, you can pull back those generators to the de Rham algebra of the 10-dimensional space, and they will become form fields on the space. And so this is what phi1 star is. And then if you change notation to make it more in line with what physicists use, then you may recognize the equations of motion of type 2A supergravity in 10 dimensions, written probably in more familiar terms through the H and F fields. Okay, so this is again those equations which actually which are used in 10-dimensional supergravity, in type 2a 10-dimensional supergravity, are obtained for free from this Sullivan minimal model. And this is another part of this generalization of the hypothesis H. Okay, so and actually the amazing thing is that this goes on for all values of k. No matter how many reductions you take, the equations of motion become more and more complicated. There are more and more basic fields of your theory, and there are more equations of motion describing the dynamics of M theory in reduced dimensions. And all of these complicated equations follow just one topological scheme, which is largely, or algebraic topological scheme, a very simple recipe of how to generate those equations of motion. Okay, yeah. So, moreover, this generalized hypothesis H leads to what I may call principal H. And it will be different H's, different things labeled by H in my talk today. So the principal H says that any feature or statement about the Sullivan minimal model of the k-fold simplification of S4 may be translated into a feature or statement about the compactification of M theory on the k-torus Tk. And even though it sounds probably wild, but the statement is actually correct, because basically this, I mean, you may easily believe that the statement is correct, because the minimal Sullivan model of this k-fold simplification carries exactly the equations of motion of the reduction of supergravity to 11 minus k dimensions. So whatever you can say about those about the Sullivan model is actually exactly what you can say about the equations of motion of supergravity in 11 minus k dimensions. So this is some of the guiding principles of this theory, and now let me explain why there is, well, let me give you some twist on hypothesis H and explain the unreasonable effectiveness of hypothesis H, speaking using the words of Wigner about this. So that there are adjunctions, actually. Let me look at this hypothesis H from the point of view of adjoint functors or adjunctions. In topology, there is an adjunction like this. Here map stands for just the set of continuous maps from one space to another. So there is an adjunction which basically says that E of x, which is taking the total space of a principal S1 bundle over a given base x, and a given base x is considered to be coming with a map to BS1, to the classifying space of S1, which is CP infinity. So this functor of taking the total space of the principal S1 bundle is a left adjoint of the functor of cyclification. So this equation basically says that this is the case. And this is something that Braunak, Meyer, Satie, and Schreiber noticed in 2018. And they say that, well, yeah. So how do we understand it and why is it important? I will tell you on the next slide, perhaps. But yeah, in a way, this explains why this. For instance, remember I started with those maps phi, with the map phi to from the 11-dimensional space to the 4th sphere, and then said that phi1 is induced by this map. So actually, one explanation of why this phi1 is induced by this map is the following. Let's think of of the 11-dimensional space-time as E of x. Indeed, S1, we assumed S1 acts on it freely, so this means that it's the total space of principal S1 bundle over some base, namely over the quotient 10-dimensional space. And so this is the 10-dimensional space-time. If you apply this for z equals to the sphere S4 and take the map phi, which belongs to this set on the left-hand side, then the map phi1 will be coming from by this natural isomorphism, natural bijection between those sets, will be a map from the 10-dimensional space, the quotient, the base of this principal S1 bundle, to the cyclification of the fourth sphere. And this is how you get all of the remaining maps phi2, phi3, and so on from further reductions of your space-time to further cyclifications of the sphere. And then, so I want to remark that this property determines this cyclification construction, in fact, the cyclification functor, and in particular, what the cyclification of a space is up to unique homeomorphism over BS1, in the category over BS1 of spaces with map to BS1. Now, in algebra, there is an incarnation of it, and it's important because we are talking about rational homotopy theory. So rational homotopy theory classifies spaces up to rational homotopy via differential graded commutative algebras. And so if you basically, you may think of, say, a path to the world of algebras from this junction, apply the functor of minimal models, and you will get another junction. But this junction exists in the category of differential graded commutative algebras, and this is something that you don't need to obtain it from topology. It's just a piece of algebra over here. So here we are talking about, on the left-hand side, homomorphisms of differential graded commutative algebras from M to an algebra, another DGCA N, divided by the ideal generated by a certain W. This W comes from the fact that N actually was taken from the category of differential graded commutative algebras over R of W. R of W is the algebra of polynomials on a two-dimensional generator. Here, W is just an abstract variable of degree 2. It corresponds to the cohomology of CP infinity or BS1. This is why it appears here. So when you consider differential graded commutative algebras over this R of W, over the algebra R of W, it's equivalent to talking about spaces over BS1 in rational homotopy theory. So then there is this adjunction, and it basically predicts what you have to put. Well, I mean, the adjunction is, if you take, there is a certain functor, which I call VP, or the Vigier polarization, of M, of another differential graded commutative algebra. So there is this adjunction, but if in principle, if this adjunction exists, then it uniquely determines what VP is. And this is, I think, is also important. This is why here, it doesn't really matter what the cyclification is. It's uniquely determined by this adjunction. So you don't really need to understand the construction of this cyclification. But it's important that it's something that you put for this injunction to be true. Here is the same story. The Vigier polarization of a differential graded commutative algebra is a certain differential graded commutative algebra that you obtain by so that this adjunction takes place. Okay, so and again, this property determines this Vigier-Poirier algebra of M of another differential graded commutative algebra up to unique isomorphism of differential graded algebras over this algebra R of W. And so the translation between those two things is that we take the Sullivan minimal model of the space Z to pass from part 1 in topology to part 2 in algebra. You take the Sullivan, oops, yeah, I wrote MZ. Yeah, it shouldn't be MZ. There is a typo here. So this should be, n should be m of x. So n is the Sullivan minimal model of x, of the space x. R of w is actually the Sullivan minimal model of BS1 or CP infinity. At the same time, it's the cohomology, but in this case, it coincides with the Sullivan minimal model. And then n divided by this ideal generated by w is the Sullivan minimal model of E of z, of the, oops, again, this should be E of x. And then here, the Vigier polarization of M is the Sullivan minimal model of the cyclification LC sub z. So there are those two important adjunctions, and now I'm transferring those adjunctions from topology and algebra to physics. And lo and behold, here is what we have. This is number 3. The adjunctions that were on the previous slide are here, but here, how can we interpret those adjunctions? Actually, in M theory, what we have is that we have a similar statement that there is a bijection, kind of natural bijection, between M theories, well, I should have put maybe on X, not in Ex. So M theories on this space, on the space-time, which I called E of X. Remember that X was the base of an S1 principal fibration, and this is the total space. So M theories on this space, think of it as, say, M theory before reduction. And then there is a natural bijection between M theories before reduction and reduced M theories on X. So this bijection is, well, first of all, here we are talking about not just fully fledged M theories. We are talking about the supergravity limit of those, and moreover, we are talking about the duality symmetric formulations thereof. So so we are not including the metric. The metric comes as extra data with extra constraints coming from the metric, associated to the metric. But as was discussed already in Hisham, when Hisham was talking about this in the morning, this is so what we are talking about is some background for supergravity, some kind of topological background for supergravity, or rational homotopy theoretic background for supergravity. When you study this background and then you put metric on top of this, and the corresponding constraints related to the metric as well on top of this. So in a way, what we are talking about are somewhat more fundamental than comes later in fully fledged supergravity and then M theory. Okay, so yeah, so the statement is that you can interpret those adjunctions as the fact that you look at M theories, the set of M theories on the space before the reduction, and there is a correspondence, a bijective correspondence, a canonical bijective correspondence, a natural bijective correspondence with reduced M theories after the reduction, on the space after the reduction. And here's the translation. Yeah, and again, this property, this bijection, basically determines what those reduced M theories are, and this explains perhaps the power of hypothesis H and why it is true. So it offers one explanation of this, at least. So the explanation is that whatever mechanism tells you how to design this minimal model of the cyclification of a space, the same mechanism tells you how to write down the equations of motion in physics for the reduced supergravity. And I kind of think that the actual reason is the algebra, the same algebraic mechanism. I believe that actually physics in the first half of the 20th century was mostly part of mathematics, which is called differential geometry. In the second half of the 20th century, physics became another part of mathematics called integration theory, kind of fancy integration theory. And in the 21st century, or at least in the first half of the 20th century, or the 21st century, physics is part of mathematics called algebra. So really, I believe that the equations of motion after you reduce M theory to lower dimensions actually are written down for algebraic reasons. Written down as they are for algebraic reasons. And this is an explanation of why this happens. Okay, so, and here is, yeah. So a way to translate from part 2, for example, from this algebraic statement adjunction to this statement is the following, that an M theory defined on a space-time X is nothing but a DGCA homomorphism from the minimal algebra, from a certain differential graded commutative algebra M to the de Rham algebra of this space. So this is what an M theory, well, the supergravity part and even this pre-supergravity part, the duality symmetric part, supergravity part defined on the space-time is exactly a differential graded commutative algebra homomorphism from a certain DGCA M to the de Rham algebra. The certain DGCA M, when X is the 11-dimensional space-time, is the minimal Sullivan model of S4. Which is this very simple algebra generated by two generators, G4 and G7, with the corresponding equations, resembling the equation or repeating the equations of motion. So, but for further reductions, when X is a further reduction of the 11-dimensional space-time, then it will be a different DGCA, namely the minimal model of the k-fold simplification of S4. And so, but this is a consequence of this translation, actually. You know, you iterate those adjunctions, you passed from, this is just a one-step reduction by one dimension, by the action of S1 on, like compactification along one variable of M theory. And you iterate this construction, you get several things, but you remember that we've started with, when X was 11-dimensional, we've started with this minimal algebra, minimal Sullivan algebra M, which was the Sullivan minimal model of S4. That's very simple algebra. Okay, now here is a recipe of writing the equations of motion, which is based on the previous. A recipe of writing the equations of motion of dimensional reduction of supergravity or M theory. So this is what I call the Vigier polarization of M theory, because it's based on the identification of this algebra or the minimal model of the cyclification or this algebra VP of M in classical rational homotopy theory by Vigier-Poirier and actually Bourgelat, but maybe I should have called it Vigier-Poirier Bourgelatization of this. So here's the Vigier polarization of M theory. In M theory on the space-time X, if M theory on the space-time X is given by those form fields G1, G2, and so on. Well, again, in physics, the notation changes depending on the dimension. Like suddenly, when you reduce the 11-dimensional theory, the equations become, the form fields, names become H's and F's. But here I'm using G's. So capital G's as opposed to what happens on the universal target spaces. Suppose that M theory on the space-time X is given by form fields G1 and G2 with the equations of motion given as the differential of the corresponding basic field is represented as a polynomial like wedges, sums of wedges of the same basic fields. then its reduction on its one-dimensional reduction will be given by form fields, but this happens for any space-time of any dimension, so you can iterate this construction. The dimensional reduction happens, is given by form fields. You take the old form fields and you add copies of them, like formal copies of them of degree 1 less, and add another form field of degree 2. And the equations of motion will become written like this, coming out of what we had before, out of the equations of motion, using the same right-hand sides of the equations of motion of the original theory. And here S, well, you need to be able to apply S to a polynomial like pi of the basic form fields. And to do this, because S originally was defined only on the basic form fields, on the generating form fields, to do this, you extend it as a square zero derivation of the algebra of polynomials in those variables G1, G2, and so on. Okay, so this is a recipe on writing down the equations of motion of a reduced theory of supergravity in any dimensional reduction. So this is the iterative step of how you do it. Okay, now, well, the title of my talk, so far I have been speaking about hypothesis H, basically, about some kind of different view on hypothesis H, and try to explain why the generalization of it to further dimensional reductions works. So, but the title of my talk was actually dedicated to the EK symmetry of reductions of M theory. And so to move to the EK symmetry, I want to consider to replace the simplifications that I have been discussing very excitingly in the first half of the talk with toroidifications. There is some subtlety in how you may go about those simplifications, which actually is not really there at the level of dimensional reductions of M theory when you mod out by one copy of S1, then another copy of S1, and so on. It doesn't really matter whether you mod in several steps, iteratively, one S1 at a time, or whether you mod out by the whole torus, like say three-dimensional torus, T3. So it doesn't really matter and there, but on the side of those universal targets, target spaces for those theories, there could be a different variation of the process. Namely, you can consider, instead of doing iterative simplifications, you might do something like go through k steps at once. And it works slightly differently. So, and we call this model the toroidification of S4. So you take the k-fold free loop space of S4, which is iterative or not iterative, is the same thing for the free loop space. It's the space of maps from the k torus to S4 in any case. But then, but when we're doing simplifications, each time we mod out by S1, we consider the free loop space maps from S1 to the targets to S4 or to the next space. Each time we were doing this, we were modding out by S1. Here, we first take the k-fold free loop space of S4 and then mod out by the action of Tk. And again, like an Ursus talk, this is the homotopic quotient, or which you may do by the Borel construction, by the k torus. Okay, so the difference between simplifications and toroidifications is in this table. So here we were iterating the simplification construction, modding out by taking this homotopic quotient by the action of S1 one at a time. And here on the right hand side we are doing first taking the free loop space k times and then modding out by Tk. Physically, the difference is slight, but there is a difference. Namely, again, I'm appealing to looking at the Sullivan model and minimal model of those spaces, the simplification on this side and the toroidification on this side, and the reading of physical information from there. I was trying to convince you that the equations of motion can be read off from the Sullivan minimal model of those simplifications. And here, but also you read off the fields as well. And here you get more fields, namely more fields of degree 1, which corresponds to axions. For example, this field, which could be thought of, well, in the previous notation, could be S2 omega 1. When you do iterated simplifications, it makes sense to write down those indices. Like this is what you get after the first simplification, this omega 1 on the previous page. And after the second simplification, you also get omega 2 as well, for example, but you get also this field S2 omega 1, which is a field of degree 1, corresponding to an axion. But in toroidification, you won't get those fields. Those will be missing. But on the other hand, you will still have some axions. For example, when you apply 3 operators, S3, S2, S1 to G4, you get a form field of degree 1, which corresponds to an axion. As concerns symmetries, and this is what I wanted to discuss, sort of the symmetries of the minimal models of those universal target spaces should be interpreted as symmetries of equations of motion of the corresponding reductions of M theory. And if you look at toroidal symmetries, namely only abelian symmetries of those equations of motion, or in other words, of the minimal model of those spaces, or the rational homotopy type, symmetries of the rational homotopy type of those spaces, then they will get the same toroidal symmetries, irrespective of whether you consider cyclifications or toroidifications. But when you look at more non-abelian or non-commutative symmetries, then, it should be more written on the right-hand side. Sorry, yeah. Less and more should be interchanged in this page. And this is why I'm talking about toroidification, because it has more non-commutative symmetries as opposed to cyclification. So in cyclification, those copies of S1 that show up, they show up not on an equal footing, whereas in the toroidification model, all of those copies of S1 show up exactly in the same way. And so there is some also symmetry between them, and this is why I want to pass to toroidification now. So at the level of minimal models, we have seen a recipe on the previous slides on how to construct the Sullivan minimal model of this k-fold simplification of S4, and this is this Vigier-Poirierization, the k-fold Vigier-Poirierization of the minimal model of S4. Now, on the toroidification side, there is also a construction on how to construct the minimal model, the Sullivan minimal model of this k-fold toroidification of S4, and I may call it the Voronavization of the minimal model of S4 for the fun of it. But so there is this construction which is similar coming from another adjunction, just a very simple, straightforward generalization of the previous adjunction. So the previous adjunction was for algebras, differential graded commutative algebras over the algebra of polynomials in 1 degree 2 variable, and here, I should have put here RW1, W2, and so on, WK, sorry. I have been preparing slides at the very last moment. So it's R of W1 through WK here. So you consider on this side the category of algebras over the algebra of polynomials in several variables. This corresponds to the minimal model of BTK, or which is the product of k copies of CP infinity. So it's the same as the cohomology of CP infinity to the power k. So you have to consider algebras over differential graded commutative algebras over are of this algebra of polynomials in k variables on this side, and on this side you're considering just differential graded commutative algebras over the reals. And then there is the disjunction, and this disjunction basically determines what a formula for this SV of x sub k of m, which allows you to compute the Sullivan minimal model of the toroidification of a space, not only S4, of any space, starting from the Sullivan minimal model of the space, in this case S4. And here is an example. I won't give you the general recipe. It's very similar to the previous recipe that was on the slide here. And again, the whole point is that you can read off what happens in rational homotopy theory, read off and translate it into equations of motion and basic fields, like it was done on this slide. So on this slide, I wrote down a recipe for writing down the equations of motions of supergravity in reduced theory, and it comes exactly from the corresponding theorem in the world of algebras, how to design a VP of M given M. So here's what we get on how to design in the corresponding world of toroidifications, how to design SV of M on this side. And this is the example when you, this would correspond to the theory in 8 dimensions, to the reduction of M theory to 8 dimensions. And if you make those letters capital and change W to omega, you will get equations of motion, but with fewer axions, as I said, because this corresponds to toroidification. Okay? Now, again, speaking about the EK symmetry of those equations of motion, so we'll be talking about now toroidifications instead of cyclifications. But to speak about the EK symmetry, I want to remind you about the EK series. So the EK Dynkin diagram looks like this in general, and it corresponds to the Cartan matrix. You can generate the Cartan matrix from it. It's basically the negative incidence matrix of the graph, of the Dynkin graph, and except that you put a number 2 on the diagonal everywhere. And this is this example. I will be talking about k greater or equal to 3 because those diagrams for k less than 3 degenerate to something interesting but less uniform. So here's the list of what you get for in relation to the whole EK series, starting from k equal to 0 up to 10, and you can go on as many times as you wish. Probably it wouldn't be physical because you don't want to reduce to negative dimensions of the space-time. So here's the table with the universal target spaces in the toroidification model. There is an outlier here, 2b, the universal target space 2b, which corresponds to the type 2b string theory in 10 dimensions. And there is a space, but it's not one of those spaces. There is a corresponding space that you may talk about, but it's not one of those spaces. And it's an outlier as you expect. It kind of corresponds to this node of the Dynkin diagram. Okay, and then the corresponding type of EK algebra for lower values of k, it's not those EKs are recognized as those concrete examples of A1, A2 cross A1, A4, D5, but then it goes into E6, E7, E8, and so on, into more familiar grounds. The Lie algebras which correspond to that are on the right-hand side. When k exceeds 8, we'll be talking about affine Kac-Moody algebras and hyperbolic Kac-Moody algebras. And it continues, it goes on through higher dimensions. It will be always hyperbolic, starting from k equals to 10. Okay, and then the Lie algebra of type EK, I want to discuss basically infinitesimal symmetries of the equations of motion, of the duality symmetric equations of motion of supergravity reduced to 11 minus k dimensions. And for that, I will define an action basically of some algebra closely related to a Lie algebra of type Ek, and this will be, we can think of the Lie algebra of type Ek, which is basically determined by this combinatorial data, the Dynkin diagram, the Cartan matrix. But a little bit more precisely, what we will be talking about is a trivial central extension Gk, which is denoted by Gk, of the split real form Ek of K of the Lie algebra Ek of type Ek. Okay? To be more precise, but we'll think of this as basically Gk is more or less the same algebra as Ek, except it's over the reals, and except that it's centrally extended Ek. It's a Lie algebra of dimension 1 or larger, and you add something to the center, which makes sense for some reason here. So so this Lie algebra Gk is defined by the Chevalley generators, E1 through Ek, F1, F2, and ... if Fk, and the elements of Hk, which will play, it's a K plus 1 dimensional space, which I've included the center into this Hk, and this is the Cartan subalgebra of this algebra. This will be play the role of the Cartan subalgebra. So you start with this real vector space Hk of dimension k plus 1, then you assume that you have a set of k linearly independent elements, sort of co-roots of this sitting in this k plus 1 dimensional space, and k linearly independent elements of the dual space, which you think of as simple roots, alpha I, and those are alpha I check. And in such a way that they satisfy those relations, like the evaluation relation given by the Cartan matrix. So Cji is the transposed Cartan matrix. Well, actually, transposed doesn't really matter, so because it's symmetric in this case. Okay, so you take this data and then define a Lie algebra by those generators and those relations, the Chevalley generators and the standard relations on how the Cartan subalgebra acts everywhere, how those elements Ei and Fj commute, and the Serre relations. So this defines an algebra. Well, if you didn't take the k plus 1 dimensional space, it would be exactly the real version of the Lie algebra Ek of type Ek, the split real version. But we added just one element to the center. Okay, and then the first statement will be about the action of a parabolic subalgebra Pk of this algebra, and the statement is that that a parabolic subalgebra, which is almost as large, it's a maximal parabolic subalgebra of this algebra, which the statement will be that it acts on the minimal model of the k-fold toroidification, which means that it acts on the equations of motion of the 11 minus k dimensional supergravity. In physics, people often talk about an action of a Borel subalgebra of symmetries, of a Borel subalgebra of symmetries of type Ek, and a parabolic subalgebra is something larger. A Borel subalgebra is also a parabolic subalgebra, but it's a minimal parabolic subalgebra. And here, actually, something larger acts, so the result is even better than what usually physicists, what shows up in physics literature. So we have this parabolic subalgebra, which is generated by all the generators but E1. So we just, this parabolic subalgebra misses only one generator out of this list of Chevalley generators. We only skip the E1 generator and get the subalgebra generated by those by the remaining generators, and of course the Cartan subalgebra, and then it acts on the minimal model of the k-fold toroidification of S4, Here are the formulas. Here is how F1 acts on all the generators here. It acts by linear automorphisms of this differential graded commutative algebra. You know, it acts, here we write down how it acts on generators. So basically, I mean, these are explicit formulas, but they come from the fact that, all of those, well, let me say for short that it comes from counting weights. Like we actually do know weights with respect to the Cartan subalgebra of all of those generators of the toroidification model of S4, and then we then there is not very much freedom in choosing on how those generators of this parabolic subalgebra act on the basic on the generators of the minimal model. Okay, so in the physics, the action we'll be talking about would be an action on form fields. Like you replace G4 with the corresponding form field, probably F4 in reduced theories. G7 is replaced by H7, and then you have this action of almost of the whole Lie algebra EK of type EK, but a little less. Okay, and here are the formulas. Okay, so then, well, it's customary in math talks to finish with main theorems. So the two main theorems related to the EK symmetry of the equations of motions are the following. So we are looking at the EK symmetry. The statement is that there are EK symmetries of the universal. What should I say? There are certain EK symmetries of the equations of motion, and those are obtained through looking at symmetries of the universal target spaces for those reduced M theories. And the statement is that the above formulas on the previous slide define a linear action of the parabolic Lie subalgebra pk of gk on the Sullivan minimal model of this space, and which means there is a Lie algebra homomorphism. This Lie algebra acts by derivations of this minimal model. In rational homotopy theory, it would mean that it acts by infinitesimal symmetries of the corresponding universal target space of this toroidification EKS4. Okay, but actually, another amazing statement is that the action of the parabolic may be extended to an action of the whole Lie algebra GK by linear graded derivations in this road, in a little bit derived road. That is, one can consider. So these derivations were actually symmetries of the minimal model. So these were not only symmetries of the generating sets in a way, but also not only symmetries of the algebras, but of the differential graded commutative algebras. So there were symmetries. Okay, thank you. Yeah, I'm almost there. Symmetries which respect the differential. So in rational homotopy theory, this rewrites as symmetries of the rational homotopy type. But one can also consider a larger differential graded Lie algebra of derivations by looking at all derivations as of those graded commutative algebras as graded commutative algebras without regards to the differential, that is not necessarily respecting the differentials, and then you get a differential graded Lie algebra of differentials of derivations, and then you may extend the action of GK by to this degree 0 component of the differential graded Lie algebra of graded derivations of the minimal model. So there is this diagram, a commutative diagram of Lie algebra homomorphisms. So this was the action of theorem 1, and here is how it extends to something bigger. So they're 0, they don't respect the differential necessarily, but they are part of the differential graded Lie algebra of derivations, sort of a differential graded a derived model of the previous derivation Lie algebra in theorem 1. And I wanted to say a few words about the meaning of theorem 2. So basically, if you look at if you're now in the world of differential graded Lie algebras, then you have some arbitrary differential graded Lie algebra L dot, then its zero-degree component plays the role of the gauge Lie algebra in deformation theory governed by this differential graded Lie algebra L dot. And in the case of Sullivan minimal models, this DG Lie algebra of derivations therefore describes the deformation theory of the Quillen minimal model, Q of X, as an L-infinity, deformation theory as an L-infinity algebra. So in the case of the k-fold toroidification, the Quillen minimal model is just the graded Lie algebra. It's not, the differential is just zero. The rational homotopy Lie algebra of the space with respect to the Whitehead product. Whitehead product was mentioned in Urse's talk. And from the physics perspective, then, the Lie algebra GK from theorem 2 acts by gauge transformations in the L-infinity deformation theory of the gauge Lie algebra, of this gauge Lie algebra of k-fold toroidification of S4. But you may think of this gauge Lie algebra as the reduction, as the gauge Lie algebra of the reduction of M theory on the N torus TK. Namely, this gauge Lie algebra is may be thought of as a k-fold dimensional reduction of the M theory gauge algebra corresponding to this topological gadget. And this is just this M theory algebra, which has two generators, one in degree 3, one in degree 6, and satisfies those commutation relation in which you can recognize the gauge algebra of M theory, of 11-dimensional M theory. And so then the point is that there is some kind of, this derived action of GK that we see in theorem 2 is actually an action by gauge transformation in the L-infinity deformation theory of the corresponding gauge Lie algebra, which corresponds to reductions of dimensional reductions of M theory. This algebra generalizes to dimensional reductions of M theory through, well, again, it's related to topology through the Quillen model, and like this, and this algebra actually, it becomes much more complicated, and and somehow this, the meaning of this theorem is that GK acts by gauge transformation of deformation theory of the gauge algebra of M theory. So it's gauge transformations of some deformation theory of the gauge Lie algebra of the reduced M theory. And that's it. Thank you.
Time for a very quick question.
Sasha, I have a question about the degree of of omega in your
2.
Yeah, but is it related to the rank of the isometries of S4 or not? Because I mean, S4 you can write it as SO5 over SO4, so essentially you've got rank 2 isometries. So what's the origin of these two? Might be related to the symmetries of S4?
I don't think so. This omega or W, it shows up only after you take simplifications. So it actually comes from S1 that shows up in simplifications, or the S1 that shows up in the reduction, in the dimensional reduction or compactification of M theory. So it's related to S1, namely this omega corresponds to the Euler class of the corresponding principal S1 bundle, okay, that the space-time forms over the reduced space-time.
Yeah, a second question is about, because in some point maybe you said that X was 10-dimensional, then in other points that was space-time was 11-dimensional.
Right.
So the map is from 11 dimension to S4?
Yeah, this would be the first. Oh yeah, the map to S4 is from the 11-dimensional space. Then you reduce the space. You consider dimensional reductions, and you get the 10-dimensional space-time, then the 9-dimensional space-time.
Yeah, I understand. But the starting, of
starting
course, is the space-time.
The starting
of
point,
MTR.
which is called hypothesis H, is a map from the 11-dimensional space-time to S4. And this is where W doesn't show up. W shows up only in 10 dimensions when you make your first reduction.
Okay, thank you.
Thank you.
Let's thank the speaker again. Thank you very much.
Thank you.